How are you all doing this morning?
Yo,
Cool deal. Does anybody have any questions regarding any homework problems or anything like that before we jump into the in-class assignment? Alrighty, then let's see here. There we go. All right, so today's in-class assignment and the next two in-class assignments will actually all be on an extraordinarily similar topic. Called the first order response circuits. And so first order circuits are those that contain a single inductor or a single capacitor. And the first problems that we're dealing with are what are called natural response problems. And they're called natural response problems because in every case, the source is effectively switched out of influencing the behavior of the energy storage element, whether it's an inductor or a capacitor, the source is no longer affecting it. So what I mean by that, if we look in this first problem, the switch is closed for all time up to t is equal to 0 minus, which is going to cause, let's see, 18 volts divided by 8 kiloohms, some amount of current flowing through that 12 millihenry inductor, which means the inductor is storing some energy. Well, when that switch opens, the source is no longer contributing anything, and all of the energy stored by that 12 millihenry inductor will be dispersed and converted to heat through the 8 kiloohm resistor and the 4 kiloohm resistor. So it's a natural response problem when the source is taken out of the circuit. And that's going to make our analysis a little bit easier. It's not significantly easier than what's called a total response problem, where sources are switched in. It just effectively eliminates one step of the analysis process. So we're going to approach all of these problems in a very formulaic way. We are going to analyze our circuit at t is equal to 0 minus, then analyze the circuit at t is equal to 0 plus, and then plug our results into the generic formula. So at t is equal to 0 minus, I'm using an odd color here. At t is equal to 0 minus, our circuit is going to look like this. So we're going to have our 18 volt source. Our switch is closed, so it's going to look like a short circuit. Then we have a 4 kiloohm resistor. Since we are at DC steady state, our inductor is going to look like a short circuit as well. We have an 8 kiloohm resistor here. And here is our voltage of interest at t is equal to 0 minus. So I'm going to label that as V at 0 minus. And here's where our current will flow. So I'm going to call that I at 0 minus. So how could we go about calculating either of these two quantities, V at 0 minus or I at 0 minus?
V at 0 minus would just be 18 volts since the resistors are in parallel.
Exactly right. So V at 0 minus is simply 18 volts, no problem there. Excuse me. How do I determine I at 0 minus? So based on what the gentleman who just spoke said, the 18 volt drop occurs over the 4 kiloohm resistor and the 8 kiloohm resistor. The current I at 0 minus is the current that's flowing through the 8 kiloohm resistor, right? Because the inductor and the 8 kiloohm resistor were in series. So we should just be able to use Ohm's law here. So we would have 18 volts divided by 8 kiloohms is 2.25 milliamps. So the actual circuit analysis that we're going to have to do on most of these problems, especially first order circuits, which is the only thing we're going to be dealing with in circuits 1, is actually pretty straightforward. Things might get a little bit weird if we had a dependent source in the mix, but for the most part, things are pretty straightforward. All right, so now we'll analyze the circuit at t is equal to 0 plus. Now it's important to note that at t is equal to 0 plus, this is the beginning of our transient condition. So this is the moment in time where things start to change, which inherently means that we are no longer at DC steady state. So we can no longer use our DC steady state model for our inductor in this case. So we're going to have to adjust. So we're going to have our 18 volt source. An open circuit. Here's our 4 kilo ohm resistor. And here is our 8 kilo ohm resistor. And what I'm going to do for the inductor, so we know at this specific instant in time that the inductor is carrying a current of 2.25 milliamps because the inductor current cannot change abruptly between t is equal to 0 minus and t is equal to 0 plus. In doing so, it would cause an infinite transfer of energy, which cannot happen, literally violates the laws of physics. So since the inductor is carrying a constant current at this and this only instant of time, and the voltage drop over the inductor will be whatever it needs to be, I'm going to model the inductor as an independent current source because it's supplying a fixed amount of current and the voltage is whatever it needs to be. The direction of the current source will be the same as the indicated direction of our inductor current I. So if I is flowing from left to right, our current through our source needs to be flowing from left to right. And if the magnitude of the inductor current at t is equal to 0 minus is 2.25 milliamps, then the magnitude of the inductor current at t is equal to 0 plus needs to be 2.25 milliamps. So is everybody okay with me modeling my inductor as a current source at this specific instant in time?
Yes, sir.
Alrighty, so here is our inductor current, I at 0 plus, which we already knew right off the bat. I'm just drawing it to be consistent. And then here is our voltage, V at 0 plus. So we know definitively that I at 0 plus has to be 2.25 milliamps. If this guy and this guy don't match, we have a horrible problem. So how am I going to solve for V at 0 plus?
Wouldn't it be your current source times the 4 kilo ohm resistor, and it would be negative since it's flowing into the negative terminal?
That is absolutely correct. So negative 2.25 milliamps times 4 kilo ohms. So let's see, that's going to be negative 10. No, negative 9. Alrighty, I didn't watch my video. Did I talk at all about time constants or anything like that? Or do I introduce that later?
I don't think you mentioned that.
Okay, well then we need to find what's called the equivalent resistance and equivalent inductance of our circuit. So that's our next step. So the equivalent inductance of our circuit, what's it going to be? There's
12 millihenries.
There's only one inductor, so we don't have a whole heck of a lot of choice here. So we have a 12 millihenry inductor, so our equivalent inductance must be 12 millihenries. To find the equivalent resistance, what we need to do, it's effectively the Thevenin resistance as seen looking into the terminals of the energy storage element. So we're defining the Thevenin resistance, and also another caveat here is it's during the transient condition. So in this case, that means when the switch is opened. So what I'm going to do is I'm going to redraw my circuit during the transient condition and take my inductor out and look in and find out the resistance that I see. So since I'm looking at a dead network, my 18 volt source needs to be off, so I'll replace it with a short circuit. Here's my 8 kilo ohm resistor. Here's my 4 kilo ohm resistor. And I'm looking in through this set of terminals where the inductor was. So I take the inductor out and then look and see what equivalent resistance the inductor sees. And from that, I can see that REQ should be what?
12 kilo ohms.
Right, because it's just the 4 kilo ohm resistor and the 8 kilo ohm resistor in series. Nothing crazy there. So 12 kilo ohms. So now I have all of the information that I need to plug into my generic formula. And my generic formula for a RL circuit is Y of t is equal to Y at 0 minus for all t less than 0 minus, and it's Y at 0 plus e to the minus R over L t for t greater than or equal to 0 plus. So Y here is just representing any voltage or current quantity. It doesn't matter if it's for a resistor, capacitor, or inductor, whether it's a voltage or current, it is going to behave in this fashion. So from this, our voltage function, V of t, just pulling in the data that I've collected, should be 18 volts because this was the voltage at t is equal to 0 minus. And for t greater than or equal to 0 plus, it will be negative 9 volts. So negative 9 e to the minus, so let's see, 12 kilo ohms divided by 12 times 10 to the minus 3 t volts for t greater than or equal to 0 plus. 12 kilo ohms divided by 12 millihenries is just going to be 10 to the 6. So I'm going to just rewrite this as a single number instead of a ratio, just because it's a little bit more neat. So minus 10 to the 6 t. So let's check. And yep, there we go. I can do a similar thing for my current. So what was my current at 0 minus?
2.25 milliamps.
All right, so I put that guy in here. What was my current at t is equal to 0 plus?
The same thing, 2.25 milliamps.
E to the minus, and I've already done my RL over, R over L, so I know that that should be 10 to the 6th t for all, and this should be in milliamps. For all t greater than or equal to 0 plus. So the steps that we follow for this are analyze the circuit at t is equal to 0 minus, then analyze the circuit at t is equal to 0 plus, find LEQ, find REQ, and then plug all of that information into our generic formula. It doesn't matter if we have an RL circuit or an RC circuit. This is just how we're going to approach it. It's a very algorithmic approach, and if you do the steps in the right order, you will always get the right answer. Any questions on that first problem? Groovy. Let's look at problem number 2. So in this problem, we have a switch that's opening up and it's going to leave us with a 2 kilo ohm resistor in parallel with a 300 microfarad capacitor. Okay. So it's still a natural response problem, nothing too crazy here. So let's look at it at t is equal to 0 minus again. Our switch is closed. What am I going to do with my capacitor? What's the DC steady state equivalent of a capacitor?
An open circuit.
Open circuit, absolutely correct. So there is where my capacitor was, and I'm looking for this current IR of 0 minus. So one thing that I'm not specifically asked for, but that I am going to have to pay attention to, is the capacitor voltage at t is equal to 0 minus as well. The reason why I have to pay attention to this, even though I'm not specifically asked to calculate it or anything, is because since the capacitor voltage cannot change abruptly, I need to know how to treat my capacitor at t is equal to 0 plus. So that requires some prior knowledge of what was going on there. Excuse me. All right, so how could I figure out, so I need to figure out what that IR is, and I also need to figure out what that VC is. Does anybody have any ideas on how I might solve for either of those two quantities?
For IR, you could use current division.
Okay, so using current division, I would have 4 milliamps multiplied by, so I'm treating the 4 kilo ohm resistor and the 2 kilo ohm resistor in series as one branch in parallel with the 4 milliamp source. And I'm treating the 1 kilo ohm resistor and the 2 kilo ohm resistor in series as another branch in parallel with the source. So I'm going to have 1 over 1 kilo ohm plus 2 kilo ohms divided by 1 over 2 kilo ohms plus 4 kilo ohms plus 1 over 1 kilo ohm plus 2 kilo ohms. So let me do some mental math here real quick. 2/3 of 4. So 8/3 of a milliamp. Anybody okay with that or can confirm it?
Yes, sir.
Alrighty, so now that I know that value, how can I determine the capacitor voltage at t is equal to 0 minus?
It would be that current times the 2 kilo ohm resistor.
Absolutely right. So the current IR is flowing through the 2 kilo ohm resistor. The 2 kilo ohm resistor is in parallel with our capacitor, so they have to share the same voltage drop. So that would give us 8/3 of a milliamp times 2 kilo ohms, 16/3 of a volt. My math is correct, which I believe it to be. All right, so at t is equal to 0 plus, so let me ask you guys a question. Once that switch opens up, is this portion of the circuit actually doing anything at all to the capacitor?
No, sir.
No. So I'm just going to stop drawing it because it's redundant information. Doesn't help anything. So I'm left with a 2 kilo ohm resistor through which my current IR at 0 plus will flow. And what am I going to do with my capacitor here? Anybody have any ideas?
You could make it an equivalent voltage source.
Right. So we know that at this specific instant in time, the voltage drop over the capacitor is exactly 16/3 of a volt, and the current flowing through the capacitor is whatever it needs to be. So I can put the 16/3 of a volt voltage source there, which is how I'm modeling my capacitor. And that will allow me to pretty easily determine what my current IR at 0 minus is, right?
Shouldn't it be at 0 plus?
Oh, excuse me, you're absolutely right. It is at 0 plus. Thank you. So how do I go about solving for this current?
It would just be the voltage divided by the resistance.
Yeah, just good old Ohm's law. So 16/3 of a volt divided by 2 kilo ohms gives me 8/3 of a milliamp. All right, so what is my equivalent capacitance?
300 microfarad.
What is my equivalent resistance? So if we look at the circuit at t is equal to 0 plus, and we take our capacitor out, what resistance do we see?
2 kilo ohms.
Right. So to be explicitly clear, you're 100% right that it's 2 kilo ohms. I'm going to redraw the whole circuit. Dead. So this was a 4 kilo ohm resistor. My current source is an open circuit. Here's my 1 kilo ohm resistor. My switch is opened. Here's my 2 kilo ohm resistor. Here are the terminals where my capacitor was. So I'm looking in. So this is what my circuit looks like during the transient condition, analyzed as a dead network. Very important. And I can see that between those two terminals, I have a 2 kilo ohm resistor, and that's it. All the other resistors, that 7 kilo ohms of resistance, one of the legs is open circuited, so it's not connected to anything. So 2 kilo ohms here. All right, so for a RC circuit, our generic function is very similar. We're going to have y at 0 minus for t less than or equal to 0 minus, and then we're going to have y at 0 plus e to the minus t divided by RC for t greater than or equal to 0 plus. So from this, my resistor current, IR of t, should be what? So what is my value for y at 0 minus here?
8/3 milliamps.
What is my value for y at 0 plus?
The same thing.
So let's see, I'm going to need 1 over r times c. So 1 over 300 times 10 to the minus 6 times 2 times 10 to the positive 3 gives me 5/3. This is milliamps for t greater than or equal to 0 plus. I just want to be clear here that this is 1 divided by REQ times. Anybody that maybe spaced out for a moment there. So the analysis of these problems is, in my opinion, very, very straightforward. We just apply the same algorithmic approach and we will get the right answer every single time. Let me just double check here. Yep, there we go. All right, any questions on this particular problem? Cool deal. So this guy is a little bit different of a problem. We're given a circuit and we are told what our responses are, so we know what V of t is and we know what I of t is, but we're asked to determine the values of the components. So how do you think we might go about doing that? Let's start with part A, determine the value of the resistor. And notice that we're given the values of the waveforms for t greater than or equal to 0. So really this would probably be 0 plus, just to be clear here. We know what they behave like during the transient condition. So how could I go about determining the value of the resistor R?
Couldn't you just take the voltage and divide it by the current?
Yeah, which is essentially just using Ohm's law. So I can still use Ohm's law even during a transient condition. No problem whatsoever there. So for part A, R is equal to V of t divided by I of t, which we can see by inspection. Well, let's just draw it out. 20 e to the minus 10 to the 3 t volts divided by 4 e to the minus 10 to the 3 t milliamps gives us, so these exponentials cancel out, so we have 20 volts over 4 milliamps is 5 kilo ohms. Nothing crazy there. For part B, determine the value of the inductor. How are we going to go about doing that? So in our generic equation, where about does the inductance value come into play? And we're only going to look for t greater than 0 minus just to make things easier. So we're going to have y at 0 plus e to the minus, since this is an RL circuit, it's minus R over L t, right? For t greater than 0 plus. So I should be able to see that negative R over L times t is this guy right here, right? So I know that negative 10 to the 3t is equal to negative R over L t. I can divide both sides by t. And let's see, so this will give me, divide both sides by -1. And so I get L is equal to R divided by 10 to the 3, which would be 5 kilo ohms divided by 10 to the 3 gives me 5 henries. Seem reasonable?
Yes, sir.
Alrighty. Part C asks me to calculate the energy dissipated by the resistor over the time interval from t is equal to 0 plus out to t is equal to 0.5 milliseconds. So, does anybody have any suggestions on how we might accomplish this? All right. So there are two different approaches that we can take, and I will just go ahead and walk us through both of them. Excuse me. So the first one is that since we know what the voltage and the current flowing through the resistor are, since these two elements are in parallel, even though the voltage drop is defined as the voltage drop over the inductance, that same voltage drop must appear over the resistor as well. Everybody okay with that?
Yes, sir.
The current, I of t, that's leaving the inductor will come to this node and it will try to split. But during the transient condition, the switch is opened, which means no current will flow through this resistor, and all of that current, I of t, will flow through the resistor R. Is everybody okay with that?
Yep.
So if I know the voltage drop over the resistor, excuse me, and I know the current flowing through the resistor, I can multiply those two guys together to get the power, and then I can integrate the power to get the energy. So the the resistor energy will be integral from 0 to 0.5 times 10 to the minus 3 of the product of, what is it, 20 volts? Oh, it's right there, yeah. 20 e to the minus 10 to the 3 t volts times 4 times e to the minus 10 to the 3 t milliamps dt. So let's do a smidge of math here. Dang it, my email's popping up for me. 0.5 times 10 to the minus 3. So let's see, 20 times 4 is going to give me 80 e to the minus 6 t is e to the minus, oh, excuse me, that's not right. That is not right at all. So 10 to the 3 plus 10 to the 3 is 2 times 10 to the 3 t. And my units here would be milliwatts. And so I'm just going to use my calculator real quick and see what this tells me. So I'm going to have 80 times 10 to the minus 3 multiplied by the integral from 0 to 0.5 times 10 to the minus 3 of e to the minus 2 times 10 to the minus 3 times my variable x. Let's see. It gave me an answer I was not expecting. It gave me, let's see, 40 microjoules, which is not the answer that I have there. So let me see what I punched in incorrectly. Yeah, let's keep working this mathematically then, just in case I did something dumb. All right, so if I pull my 80 out, I'm going to have 80 times 10 to the minus 3 watts. When I do that integral, I'm going to have a -1 over 2 times 10 to the 3 here. Right, okay. And this has units of per second. Then I'm going to have e to the minus 2 times 10 to the 3rd t evaluated at 0 and 0.5 times 10 to the minus 3. Excuse me. So let's see, that's going to be 80 times 10 to the minus 3 times -1 over 2 times 10 to the +3. Alrighty. And then I'm going to have that multiplied by, let's see, e to the minus 2 times 10 to the 2 times 10 to the +3, and then my time there is 0.5 times 10 to the -3. I'm getting a syntax error. What did I punch in wrong? All right, excuse me. So e to the negative 2 times 10 to the 3 times 0.5, excuse me, times 10 to the -3. All that minus 1. Multiplied by my product. There we go. 25.285 microjoules. So that's one method. And it was reasonably complicated. It was still using just our basic circuit analysis techniques and relationships, but the math got a little like me.
Hello?
Numbers into my calculators, I got really weird. Yes, sir.
Hello. You can hear me?
Yes.
So what I did in the original equation that I was working with it because it seemed good enough, was that the current that you had that multiplied by the voltage was milliamps. So you had to put 0.04 times 20, which is 0.08 instead of 80. And then everything else is the same. And then
Okay.
that's what I did to get it, and it gave me the same answer.
Yeah, I thought I pulled out an 80 times 10 to the -3, but I may not have. But yeah, so follow, no issue there yet. That's why I try to pay so much attention to the units, because if you get one little unit relationship wrong, it can mess lots of things up. But there is an alternate way that, in my opinion, may be slightly easier. So let me ask you guys a question. Based on the information that we have in these two relationships, do we have enough information to determine what the energy stored by the inductor is at t is equal to 0 plus?
Yeah.
So what's the equation for the energy stored by the by an inductor as a function of time?
1/2 times the inductance times the current squared.
Yeah, 1/2 Li squared. Okay. So we know what the waveform is, so we can figure out what the energy is as well. But if we know what the value of the energy stored by the inductor is at t is equal to 0 plus, and we have enough information to determine what the value of the energy stored at t is equal to 0.5 milliseconds is, I would argue that the amount of energy lost by the inductor has to be the same as the amount of energy absorbed by the resistor. Does anybody have any questions about that? So what I am suggesting is that the energy absorbed by the resistor is going to be the change in the energy seen in the inductor, because the inductor is what's supplying the resistor its energy, right? So we would have 1/2, what's L here? 5 henries. And let's see, I at 0 is going to be 4 milliamps. And then here, we're going to have 4e to the minus 10 to the 3, 0.5 times 10 to the minus 3 milliamps squared. So let's see what number we get. I did 4 times 10 to the minus 3. Actually, I can just multiply that by 10 to the minus 6. So for my two terms, I get 40 microjoules minus 14.715 microjoules is equal to 25.285 microjoules. So same answer using no calculus. So does, I want to be clear here, does everybody understand what I did in the second attempt?
Yes, sir.
All right. Well, it's just, you know, it's a different way of looking at the same problem that involves significantly less math. So try to apply all of your knowledge and understanding to each question to develop the most efficient route of getting an answer. If you can think about the problems from multiple directions, to me that's illustrating that you have a good understanding of what's going on. Another way, so let me revisit one of these problems real quick and see if I can think of something. No, none of these really lend themselves to it. I was going to say we could try to develop a relationship for the voltage drop across the inductor by I guess we could do that. Nah, never mind. It's not that big of a deal. I'm just going to say, you know, we have all of these differential based relationships and integral based relationships, and sometimes they can be tedious, but we can get the same result by thinking about what's going on in the circuit and just using Ohm's law, for instance. But anyway, that's neither here nor there. Just, yeah. Okay, so unless anybody has any other questions, I think we're done for the day, and I will catch you guys all on Monday afternoon.
Thank you, Dr. Hardman.
Yep, have a great weekend.
You too.